And now in this lecture we find out the area of a circle using two different methods. In the drawing we have a circle and we have also this is square ABCD. You know that line segment AP equals to 1 unit in its length. This is line segment QC. This equals to 3 units in its length. Again, our mission is to find out the area of this circle. So we start with the first method. First of all, we know that all the angles inside any square are right angles. So those 4 angles are all right angles. So this is a right angle. This is also a right angle. This is a right angle. And this is also a right angle. When you find the center of this circle, this point is point O. When you find the point of tendency of tangent AB, with this circle, this point is point S. In the next step, we join points O and S together by straight line. OS is the radius of the circle. We define the radius of this circle as x, so OS equals to x. So here we can implement rule 1. So I repeat quickly on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle and we have also tangent AB that is tangent to the circle is point M. This point M. Point M is the point of tendency of tangent AB with this circle. In addition, we have the radius OM that equals to R. The radius OM is drawn to point M that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Why? Because in our drawing we have the radius OS that is equal to x. The radius OS is drawn to point S, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO according to rule 1. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and Q together by straight line. We join points O and Q together by straight line. OQ is also the radius of this circle, is equals to x according to our definition. Again, we have the radius OQ that is drawn to point Q, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. So inside quadrilateral SOQB we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th missing angle. In total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4th missing angle must be equal to 90 degrees in its size. So inside the small quadrilateral, SOQB, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be it is a rectangle if not a square. So we relate to this quadrilateral SOQB is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SOQB, side SO must be equal to the opposite side QB, but SO is x, therefore QB must be also equal to x units in its length. Likewise, according to the sum rule, in the sum rectangle SOQB, side OQ must be equal to the opposite side SB, but OQ is x, therefore SB must be also equal to x units in its length. We also know that all the sides of any square are equal to each other. That is to say, this square ABCD, side AB equals to side BC equals to side CD equals to side DA. And especially side AB equals to side BC. So already know, in square ABCD, side AB equals to side BC. Side AB equals to side BC. AB equals to AS plus SB. Again, AB equals to AS plus SB. AB equals to AS plus SB. And you know that AB equals to BC. BC equals to BQ plus QC. Again, BC equals to BQ plus QC. BQ plus QC. So in total, we have found out that according to equation 1, AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. So we have AS plus SB. SB is x, and it is equal to BQ. BQ is also x, plus QC. QC equals to 3 units in its length, according to what is given as the question. So in total, according to equation 1, we actually found out that s plus x equals to x plus 3. Here we subtract x from this equation in equation 1, so x will get cancelled. And we left with AS that is equal to 3 units in its length. So actually, this is 97 AS that is equal to 3 units in its length. In the next step, we will do a construction. That is to say, from this point P, we will draw perpendicular on SO. Again, from point P, we will draw perpendicular on the radius SO. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So, inside the small quadrilateral, in the next step, we define the point of tendency, we define the touching point of the perpendicular from point P and SO. This point is point N. So actually, inside the small quadrilateral A, P, and S, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this fourth missing angle must be equal to 90 degrees in size. So inside the small quadrilateral A, P, and S, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle if not a square. So we relate to this small quadrilateral A, P, and S as a rectangle because it has 4 right angles. So this is a rectangle. Quadrilateral A, P, and S is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle AP and S, side AP must be equal to the opposite side NS. But AP is 1, therefore NS must be also equal to 1. Likewise, according to the sum rule in the same rectangle AP and S, side AS must be equal to the opposite side PN, but AS is 3, therefore PN must be also equal to 3 units in its line. In the next step, we join points P and O together by straight lines. PO is the radius of this circle that is equal to X. So in the next step, I'll copy the right green triangle P and O in the new page, and we'll implement the Pythagoras theorem in this right green triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. But before that, what is the length of line segment NO? From the drawing, it is very easy to see that NO in total equals to SO minus SN. So it is down, NO equals to SO minus SN. So NO in total equals to SO, that is X, it is the radius of the circle that is X, minus SN. We just write down further that SN equals to 1. So in total, NO equals to X minus 1 unit in its line. This is line segment NO, that is equals to X minus 1 unit in its line. Pn equals to 3 units, and therefore PO equals to X units in its line. Here by PT is the relation for Pythagoras theorem. So actually, this is the right green triangle P and O that I copied from the original drawing according to the Pythagoras theorem. In this right triangle P and O, PO squared, that is the square root of the hypotenuse, equals to PN squared plus NO squared. So I write it down. PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. PO is X, therefore PO squared is X squared. X squared equals to Pn squared. Pn is 3, therefore Pn squared is 3 squared, that is 9. Plus NO squared. NO is X minus 1, therefore NO squared is X minus 1 squared. So in total we shall find out that X squared equals to 9 plus X minus 1 squared. We'll open the brackets of this expression, and we get that X squared equals to 9 plus X minus 1 squared. X minus 1 squared equals to X squared plus 1 squared, that is 1, minus 2 times X times 1, that is minus 2X. So here we have X squared on both sides of the equation, so X squared will get cancelled. After we cancel X squared, this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10, minus 2x. So in total we shall find out that 0 equals to 10 minus 2x. Here we add 2x to this equation, and we get that 2x equals to 10. So here we divide this equation by 2. Finally we get that x is the length of the hypotenuse PO, and x is also the radius of the circle. X equals to 10 over 2, that is 5. So I shall find out that the radius of this circle equals to x that is equal to 5 units. Our mission is to find out the area of this circle. So the area of any circle is equal to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, I should found out that the area of our circle equals to pi x squared. X is 5, therefore x squared is 5 squared, that is 25. So in total, the area of our circle equals to 25 pi square units. So in terms of numbers, the area of our circle equals to 78.54 square units. So repeat again, we found out that the area of the circle is equal to either 25 pi square units, so in terms of numbers, the area of the circle equals to 78.54 square units. So we finished with the first method. In the next step, I will present to you how to find out the area of the circle according to the second method. First of all, we know that all the angles inside the square are right angles, so those two angles are all right angles. So okay, this is a right angle. This is a right angle. This is a right angle, and this is also a right angle. We define the center of this circle, this point, as point O. We define the point of tendency of tangent AB with this circle, this point, as point S. In the next step, we'll focus on this point B. Point B is a common external point in relation to this circle. So for the common external point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. So I click quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing, we have a circle. This is the common external point P. From this common external point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. So can I actually implement rule 2 in our drawing? Why? Because in our drawing, from the common external point B, we have two tangents to this circle, tangent BS and tangent BQ. And according to rule 2, they are equal to each other. So I write it down. The length of tangent BS is equal to the length of tangent BQ according to rule 2. So if we define the length of this tangent BS as x, then the length of this tangent BQ must be also equal to x because they are equal to each other according to rule 2. We also know that all the sides of any square are equal to each other. So therefore, in square ABCD, side AB equals to side BC equals to side DC equals to side DA. So in square ABCD, side AB equals to side BC. So I'll write it down. In square ABCD, side AB equals to side BC. AB equals to BC. In square A, B, C, D. Side AB equals to side BC. AB equals to AS plus SB. AB equals to AS plus SB. And AB equals to BC. BC equals to BQ plus QC. BC equals to BQ plus QC. And again, BC equals to BQ plus QC. So in total, according to equation 1, we found out that AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is, plus SB. SB equals to X, and it is equal to BQ. BQ also equals to X, plus QC. QC equals to 3. So in total, according to equation 1, we actually found out that AS plus X equals to X plus 3. Here we subtract X from this equation 1. So X will get cancelled, and we left only with AS that is equals to 3 units in its name. So 3. This is my segment AS that is equal to 3 units in its name. So I write it down, AS equals to 3. In the next step, we'll extend line segment AD by straight line until it touches the circle. And when we find the touching point of the extended line segment AD with this circle, this point is point M. In the next step, we will focus on the common extent point A. From the common extent point A, we have tangent AS, and from the same common extent point A, if we draw a straight line, we get here chord PM. And therefore, we can implement here rule 10. So repeat equal rule 10. According to rule 10 is true in any circle. So in any circle, if AB is any chord, AB is a chord inside the circle. If AB is any chord in the circle, and PT is a tangent to the circle, tangent PT is tangent to this circle at point T. So in this drawing, the following equation will be true. PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can definitely implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common extent point A, from this common extent point A, we have here tangent AS, and from the same common extent point A, we draw the straight line here, we get here chord PM. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, we will get that AS square equals to AP times AM. Again, AS square equals to AP times AM. So I write it down. So if we focus on the common extent point A, according to rule 10, we'll get that AS square equals to AP times AM. Okay, again. If we focus on the common external point A, according to rule 10, we get that AS squared equals to AP times AM. AS is 3, AS is 3, therefore AS squared is 3 squared, that is 9. And it is equal to AP. AP is 1 times AM. AM in total equals to AP plus PM. Again, AM in total equals to AP plus PM. AP plus PM. So according to rule 10, we actually found out that 9 equals to AP plus PM. So 9 equals to AP is 1, so it is 1 plus PM. So in total, according to rule 10, we actually found out that 9 equals to 1 plus PM. Here we subtract 1 from this equation, and finally get that PM equals to 9 minus 1, that is 8. So PM equals to 8 units in its length. So we actually found out that this is called PM, that is equals to 8 units in its length. In the next step, we'll do a construction, that is to say, from this point O, that is the center of the circle, we'll do a perpendicular on chord PM. Again, from point O, that is the center of the circle, we'll do a perpendicular on chord PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord PM. This point is point N. So, in conclusion, actually, draw a perpendicular ON on chord PM. Again, we do perpendicular ON on chord PM. And therefore we can implement here rule 11. So I'm clicking on rule 11. According to rule 11, the perpendicular to a chord drawn from the center of the circle bisects the chord. So in the drawing we have a circle, and point O is the center of the circle. From this point O, that is the center of the circle, we have perpendicular OM on chord AB. And according to this rule 11, perpendicular OM bisects chord AB. If perpendicular OM bisects chord AB, it means that AM equals to MB. AM equals to MB according to this rule 11. So whenever you will draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. So I can actually implement rule 11 in our drawing. One, because in our drawing, from the center of the circle, that is to say from point O, we have perpendicular ON on chord PM. And therefore, so all the requirements of rule 11 are satisfied, and therefore we can implement a rule 11. According to rule 11, perpendicular ON bisects chord PM. If perpendicular ON bisects chord PM, it means that PM equals to NM. Okay, Pn equals to Nm according to rule 11. Okay, so I write it down. According to rule 11, Pn equals to Nm. So chord PM has been bisected into two halves. Each half equals to PM over 2. Again, called PM has been bisected into two halves. Each half equals to PM over 2. So the first half PM equals to the second half NM, and each half equals to PM over 2. But we know that PM is 8, therefore PM over 2 is 8 over 2, that is 4. From this normal equation, we will derive that Pn equals to 4 units in its length. Pn equals to 4 units in its length. Pn equals to 4 units in its length. So this is line 7 Pn, that is equal to 4 units in its length. In total, An equals to AP plus Pn, that is 1 plus 4, that is 5. N equals to 5 units in its length. In the next step, we join points O and S together by straight line. OS is the radius of this circle, that is equal to x according to our definition. Actually, we doesn't define the radius of the circle, so OS, anyway, OS is the radius of the circle. ON is the radius of the circle because of the fact that it starts from point O, that is the center of the circle, and ends at point S, that is the point of the circle itself. Therefore, OS is the radius of the circle. Here you can implement rule 1. Why? Because we have the radius OS that is drawn to point S, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrilateral ONAS, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral ANOS, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, not a square. So we relate to this quadrilateral ANOS as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ANOS, side AN must be equal to the opposite side OS. OS is the radius of the circle. So side AN must be equal to side OS in rectangle ANOS. But AN in total equals to 4 plus 1, that is 5. Therefore, SO must be also equal to 5 units in its length. SO is the radius of the circle, that is equal to 5 units. In total, we found out that the radius of the circle equals to 5 units in its length. The radius of the circle equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle is equal to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. But we just right now found out that the radius of our circle equals to 5. Therefore, the radius squared is 5 squared. So in total, the area of our circle equals to pi times 5 squared. So it is pi and 5 squared is 25. So in total, we found out that the area of this circle equals to either 25 pi square units, or in terms of numbers, the area of this circle equals to 78.54 square units. So repeat again. Actually, in both methods, we found out that the area of this circle equals to either 25 pi square units, or in terms of numbers, it is equal to 78.54 square units. Again, it is equal to 78.54 square units. Okay, so in the next step, I will summarize the lecture. We'll start with the first question, of course. So in this lecture, we found out the area of this circle using two different methods. In the drawing, we have a circle and we also have square ABCD. We know that 97 AB equals to 1 unit in itself, 97 QC equals to 3 units in itself. Again, our mission is to find out the area of this circle. So first of all, we know that all the four angles inside this square ABCD are right angles. We define the center of this circle, this point as point O. We define the point of tendency of tangent AB with this circle, this point as point S. In the next step, we join points O and S together by a straight line. OS is the radius of the circle that is equal to X according to our definition. We join points O and Q together by a straight line. OQ is also the radius of the circle that is equal to X. So here we can implement rule 1. Because of the fact that the radius OS that is equal to X, the radius OS is 1 to point S, that is the point of tendency of tangent AB with this circle. And whenever your radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius OQ that is equal to X, the radius OQ is 1 to point Q, that is the point of tendency of tangent BC with this circle. And whenever your radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to the sum rule 1. So inside quadrilateral SOQB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this four facing angle, in total they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this four facing angle must be equal to 90 degrees in its side. So inside quadrilateral SOQB we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be its rectangle and not a square. So we relate to quadrilateral SOQB is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle SOQB, side SO must be equal to the opposite side QB. But SO is X, therefore QB must be also equal to X. Likewise, according to the same rule, in the same rectangle SOQB, side OQ must be equal to the opposite side SB. But OQ is X, therefore SB must be also equal to X units in its length. So in total, we found out that quadrilateral SOQB is not a rectangle but a square, because of the fact that all of its sides are equal to each other, each side of this square equals to X units in its length. Okay. In the next step, we also know that all the sides of square ABCD are equal to each other. That is to say, side AB equals to side BC, equals to side CD, equals to side DA. And especially side AB equals to side BC. So in square ABCD, side AB equals to side BC. AB equals to AS plus SB. Again, AB equals to AS plus SB. BC equals to BQ plus QC. BC equals to BQ plus QC. So in total, AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. Plus SB. SB is X. SB is X, and it is equals to BQ. BQ is also X. Plus QC, that is 3. Again, BQ is X and QC is 3. So in total, according to equation 1, we actually found out that AS plus X equals to X plus 3. Here we subtracted X from this equation and finally found out that AS equals to 3 units in its length. So this is 97 AS, that is equals to 3 units in its length. In the next step, we did the construction, that is to say from this point P, we drew perpendicular on the radius SO. from point P, we go perpendicular on the radius SO. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and SO. This point is point A. It's point N. So inside quadrangle, the small quadrangle A, P, and S, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees. And therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside quadrangle A, P, and S, we have 4 right angles. And according to rule 5, any quadrangle around the test for right angles must be the rectangle not a square. So we relate to the small quadrangle A, P, and S as a rectangle because we test for right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle AP and S, side AP equals to side NS. The opposite side NS. But AP is 1, therefore NS must be also equal to 1. Likewise, according to the symbol, in the same rectangle AP and S, side AS equals to the opposite side PN. But AS is 3, therefore PN must be also equal to 3 units in itself. What is the length of the missing 9 segment NO? NO must be equal to OS plus A, NO must be equal to OS minus NS. Again, NO equals to OS minus NS. So NO equals to OS, that is X, it is the radius of the circle, that is X, minus NS, that is 1. So in total, ON equals to X minus 1 unit in its length. We join points P and O together by side line. PO is the radius of the circle, that is equal to X. In the next step, I copy the right triangle P and the right green triangle P and O in the page, and we implemented the Pythagoras theorem on this right triangle P and O. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here this is the right triangle P and O that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle P and O, PO squared, that is the square of the hypotenuse, equals to PN squared plus NO squared. The hypotenuse PO is X, therefore PO squared is X squared, and it is equals to Pn squared. Pn is 3, therefore Pn squared is 3 squared, that is 9, plus NO squared. NO is X minus 1, therefore NO squared is X minus 1 squared. So in total, according to the Pythagoras theorem, I should found out that X squared equals to 9 plus X minus 1 squared. Open the brackets of this expression and find out that X squared equals to 9 plus X minus 1 squared. X minus 1 squared equals to X squared plus 1 squared minus 2 times X minus 2 times X times 1, that is minus 2X. We have X squared on both sides of the equation, so X squared will get cancelled. After we cancel X squared, this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 9 plus 1, that is 10. So in total, this side of the equation we have 10 minus 2x. So in total we should find out that 0 equals to 10 minus 2x. Here we added 2x to this equation, and finally found out that 2x equals to 10. Here we divided this equation by 2, and finally found out that x equals to 8 over 2, that is 5. So the radius x of this circle equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. So it is pi, the radius times the radius of our circle squared. The radius of our circle is x, therefore the radius squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 5, therefore x squared is 5 squared, that is 25. So in total, we should find out that the area that we are looking for in this question, that is the area of this circle, equals to either 25 pi square units. So in terms of numbers, the area of this circle equals to 78.54 square units. We finished with the first method. In the next step, I presented to you how to find out the area of this circle according to the second method. So, we know that all the angles inside square ABCD are right angles, so those 4 angles are all right angles. We define the center of this circle, this point as point O. We define the point of tendency of tangent AB with this circle, this point as point S. In the next step, we focus on this common extent point, point B. Point B is a common extent point in relation to the circle. For this common extent point, point B, we have 2 tangents to this circle, tangent BS and tangent BS and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BS equals to BQ according to rule 2. So if we define the length of this tangent BS as x, then the left of tangent BQ must be also equal to x because they are equal to each other. You know that all the sides of any square are equal to each other. That is to say, AB equals to BC equals to CD equals to DA, and especially AB equals to BC. In square ABCD, AB equals to BC. AB is AS plus SB. Again, AB is AS plus SB equals to BC. BC is BQ plus QC. Again, BC is BQ plus QC. BC is BQ plus QC. So in total, we can find out that according to equation 1, AS plus SB equals to BQ plus QC. AS is the missing side, so we leave it as it is. AS plus SB. SB is X. Again, SB is X. And it is equals to BQ. BQ is also X plus QC. QC is 3. Again, BQ is X and QC is 3. So in total, we can find out that AS plus X equals to X plus 3. Here we subtract X from this equation, equation 1, and finally found out that AS equals to 3 units in its length. That is to say, the length of this line segment AS is equal to 3 units in its length. In the next step, we extended line segment AD by a straight line until it touches the circle. We define the touching point of the extended line segment AD with this circle. This point is point M. If we focus on this common external point A by point A is an external point in relation to this circle. So if we focus on this common external point A, from this common external point A, we have tangent AS that is tangent to this circle point S, and if we do a straight line from point A, we get here chord PM. So actually all the requirements of rule 10 are satisfied, and therefore we can implement in rule 10. According to rule 10, we get that AS square equals to AP times AM. Again, AS square equals to AP times AM. Again, according to rule 10, AS square equals to AP times AM. AS is 3, therefore AS square is 3 squared, it is 9, and it is equals to AP. AP is 1 times AM. AM in total equals to AP plus PM. So AM equals to AP plus PM. So in total 9 equals to 1 times AP plus PM. AP is 1. So in total 9 equals to 1 plus PM. We subtracted 1 from this equation and finally found out that PM, chord PM equals to 8 units in its length. This is chord PM. It is equals to 8 units in its length. In the next step, we did the construction, that is to say, from this point O, that is the center of the circle, we do perpendicular on PM. Again, from point O, that is the center of the circle, we do perpendicular on chord PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and PM as N. So actually, we have here from the center of the circle perpendicular ON on chord PM. Therefore, all the requirements of Rule 11 are satisfied, and therefore we can implement here Rule 11. According to Rule 11, chord O perpendicular ON bisects chord PM. Again, according to Rule 11, perpendicular ON, that is from the center of the circle, bisects chord PM. If perpendicular ON bisects chord PM, it means that PN equals to NM. Okay, according to Rule 11, PN equals to NM. And because of the fact that perpendicular ON bisects chord PM, it means that it divides it into 2 halves. Each half must be equal to PM over 2. So the first half is PN, is equal to the second half, that is NM, and each half equals to PM over 2. But PM is 8, therefore PM over 2 is 8 over 2, that is 4. So from this equation, we will derive that Pn equals to 4. Again, Pn equals to 4. So this is line segment Pn, this equals to 4 units in itself. In total, AN equals to AP, that is 1, plus PN, that is 4. So in total, AN equals to 1 plus 4, that is 5. In the next step, we join points O and S together by straight line. OS is the radius of the circle. OS is the radius of the circle because it starts from point O, that is the center of the circle, and then at point S, that is the point on the circle itself. So this is exactly the definition of radius. Therefore, OS is the radius of the circle. Here we can implement rule 1 because we have the radius OS that is known to point S, that is the point of tendency of tangent AB with this circle. And whenever you have radius that is known to the point of tendency, then tangent AB will be perpendicular to the radius SO. If AB is perpendicular to SO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So inside quadrangle NASO, inside this quadrangle, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in inside. So inside quadrangle ANOS, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be this rectangle if not a square. So we relate to quadrangle ANOS as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ANOS, side AN must be equal to the opposite side OS. But AN equals to 4 plus 1, that is 5. Therefore OS, that is the radius of the circle, equals to 5 units in its length. That is to say, in conclusion, we can find out that the radius of this circle equals to 5 units in its length. Our mission is to find out the area of this circle. Actually, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. But we just right now found that the radius of our circle is 5. Therefore, the radius squared is 5 squared. So in total, the circle equals to pi times 5 squared. 5 squared is 25. So in total, we should find out in both methods that the area of this circle, that is the area that we are looking for in this question, it is equal to either 25 pi square units, or in terms of numbers, it is equal to 78.54 square units. Okay, thank you very much.